Good. Okay, well, I want to welcome you all here, and especially Samir for volunteering to do this work for us. And also I want to thank Bogdan and Nate and Sean and so on, my postdocs, for being volunteered to sort of guide us through the discussion. Anyway, I'm looking forward to today, and let's open with Samir, as I think he probably wants to make some opening remarks about what it all means. So over to you, Samir.
Yeah, okay. Yeah, thanks. Thanks to everybody for coming here. And I think today there's not much I want to say in terms of an introduction. I sort of did that last time to just lay out where we overall want to go. But I think what we are going to see in these exercises is the crux of the information paradox. In particular, the problem where you have two harmonic oscillators and then you start in an entangled state, in the vacuum state, and then you decouple them. That actually contains the entire essence of the information paradox. And so one has to just get a good intuition of that, and then just to keep seeing how it actually applies in the black hole puzzle. And the moment you ask anybody for how they have solved the puzzle, they start telling you something. You say, okay, just stop. Tell me what happened to this entangled pair. At the moment they answer that question, you know exactly what they are doing. You will know whether they have a remnant scenario, whether they have non-local physics, or whether they have a fuzzball. You just ask them what happened to this particular entangled pair, and then you know everything. So I think maybe as we discuss today about the solutions to various questions, we should keep coming back to, as you stretch something, why is entangled pairs, why are entangled pairs created, and where is entanglement happening in the black hole, and who's entangled with who. That's actually everything. So if we can understand this particular one intuitively, we really have a good hold on the entire information paradox. So maybe my suggestion was, when people are presenting something, of course, we will be sharing the screen with that. But after that, if people just want to have like a discussion, if we break the share, I was wondering if there's a way of getting the screen to look as if everybody's picture is up there so we can see everybody's faces. Maybe that way people will be able to ask questions more easily. So I don't know if there's a way in Zoom we can see everybody's faces.
Yeah, of course, it's up to you. So you can actually put, when you go to your own Zoom, you can actually press speaker view. If you go to the right up corner, you can press view, and then you can put either speaker view or you can put gallery.
Okay, very good. So, but of course, for that, whoever sharing should stop sharing first, right? Because if there's something sharing, then you can't do that.
Samir, maybe I should
do that.
Okay.
Maybe I should mention that I don't think we are as prepared as Nick last week, so we do not have certain slides to share to talk about the questions.
And that's perfectly fine. But that may be even nicer for this particular problem set, because last time there were definite answers to things. This time we actually want to just get a feeling for things. So we want everybody to just start asking questions and talking about it, because in the end, all we need is intuition. We're not actually looking for properly solved things. Those are anywhere there in the references which I gave. So if you can just kick off a discussion and then people feel comfortable asking questions. And just for that, I was saying maybe we can have a view where everybody can see everybody. I think I figured out this gallery view, right? So
I think what you should do, Bogdan, is one of you guys, take it in turns or whatever, but just saying, let's discuss problem one, and then state what the problem was, and state what the conclusion is, and have everybody sort of try and understand the basic message of each of the problems, and then we'll move on. And however you want to do it.
Yeah, just start us off in some
way. I did it prettily last time simply because I had all the slides already from a GR class, so it was elementary for me to do that. And you're starting from scratch, so okay, over to you guys. I don't know, Bogdan, Sean, Nate, whoever.
So I think the problems that we got this week are kind of like problem 1 to 4 form like a basis for us to understand the paper that was in problem number 5. So I guess the best idea would be perhaps to discuss problems in turn, like just go in order, because ideas from problem 1 were used in problem 2, and then problem 3 and problem 4. So they were, for example, just as a broad introduction, in problem 1, what we did, we started with the discrete set of masses, which we then take to a continuous limit, and then we quantize the system, which sort of acts as a model for scalar quantization of a scalar field in zero dimensions in this case, or 1, whatever. The second problem, what we did is you see that by just considering a single harmonic oscillator, by changing the frequency of the harmonic oscillator from one stage to the other in time, what you see is that the vacuum at t is smaller than 0, see that doesn't correspond to the vacuum if t is greater than 0. And this is kind of like one of the essence of the Hawkins calculation, that the vacuum at one end or at one end of the black hole is not equal to the vacuum at the other infinity. So xi minus and xi plus, the vacuum states are not the same. So you get particle creation just because something happens in between. Some non-stationary solution is in between.
Are you going to go into any more detail about the solution, or
yes, absolutely. Perhaps I think it's better to have an introduction to say like what we've done and then go through like why.
Well, fair enough. I was going to jump in and say a few things.
Yeah. Okay.
Yeah. Go ahead.
So yeah, the problem two then just tells you that by changing the frequency of the problem, but changing, for example, the parameter of in equation 17 of the problem set 2, then we get particle creation. And then problem 3 and problem 4 kind of give us a mechanism in what sense this change of frequency occurs. The first one is the cosmological example by expanding space, by changing the volume of space-time in a sudden jump. And problem 4 is by considering two coupled oscillators which become decoupled at some time. And then problem 5 was the Giddings-Nelson paper, which discusses a two-dimensional example of black hole of collapsing matter. So I suppose we should start with problem number 1. I don't know what's the best way to do this. I suppose let me just. Perhaps the best way. So it's up to the people who are in the audience. So if there's any specific questions, or perhaps another.
People should at any stage feel free to interrupt us as well, or interrupt anybody really who have questions.
Perhaps as a starting point, we can start like, are there any specific questions that people want to discuss when talking about question number 1 or problem number 1?
Do you have any means to draw online or on an iPad? Because it would help if you just drew pictures of stuff.
Unfortunately, we are ill prepared with that, so we have no way of writing.
Neither of us has a tablet.
Okay.
Yeah.
If you like, I can get my tablet connected, and you can give me artwork directions.
Yeah, well, I think problem 1 is, I mean, I don't know how many people have done QFT, but if you have done a QFT course in your life, this is the classical problem of where you start with n with n point masses connected via springs. In this case, we have periodic boundary conditions, so you can imagine the first and the last point mass are connected. And then you first take the continuum limit, where in order to start analyzing the whole thing as waves propagating on that medium, when you're taking this continuum limit, you should be careful because continuum limit is not just taking the displacement parameter going to 0, but you take a going to 0, but in the same time, you should keep n over a, where n is the number of point mass that you have fixed, and also you should keep the mass density m over a, where m is the mass of a single point mass fixed as well. Where we assume in this problem that all the spring constants are the same between all the point masses, and all the masses of the point masses are the same. And when you take this continuum limit, after that you get a Lagrangian for which you can derive the equations of motion very easily, and you get the wave equation, where this wave equation is for a scalar field, and this scalar field is basically measuring the displacement from the equilibrium positions of the springs. And you're basically become interested in macroscopic observables of how, for example, what do long wavelength perturbations of this system will lead to, and things like that. So you're not that much interested anymore in the individual displacement of each oscillator, but of how the field that describes the whole system behaves. Yes, that's what Nick has there. And after that, in typical QFT fashion, then you can go to Fourier space by whatever way you choose, whether you expand in plane waves, whether you expand in sines, cosines, however you do this. You can go to Fourier space. And when you go to Fourier space, you basically see that this system is equivalent to an infinite number of decoupled simple harmonic oscillators. And then for each one of them, you can write in the classical way, you can write define creation and annihilation operators, and define a Hamiltonian that's basically the sum of the creation times annihilation operator, an infinite sum over this, plus you get some vacuum energy that you might decide in some way to get rid of or not, depending on what you want to do in the end. I think, and then, when you define this creation annihilation operators, you define some canonical commutation relations between them. And when you commute them with the Hamiltonian, you can see that they correspond to exciting quanta with a certain momentum K that's linked in some way to the parameters of the system of springs and masses that you started with. I mean, that's the very broad picture of what's going on.
Figure it out as I go, but basically, so I don't keep going. But
I mean, I think this is a broad, the broad strokes of what you do to start from the classical system of oscillating point masses to go to continuum and then quantize the system, which is, I think, what Samir wanted us to do. I don't know whether he wanted us to go into more detail.
I've actually got a couple of notes I just made myself here, but I don't guarantee to keep this up. I mean, this is the system that you have of n masses. And that's basically the Lagrangian of the system, where these are the displacements with n plus 1 to be identified with 1 or something.
Yeah.
And then the eigenmodes are simply this, where this is the label of the oscillator, and P is the actual eigenmode label, N is the number of oscillators, and you can easily check this as an eigenmode of the system. And the eigenfrequencies are given by this, where P is this parameter. And then in the continuum limit, J over N goes to some continuum variable, I'll call it Y. And then this becomes X of P as a function of Y becomes e to the 2 pi I times what 2 pi I Y times P. And you can check the eigenfrequencies of the system are given by this. And so in the continuum limit, K goes to infinity at the same rate, I think, as N goes to infinity. And so the K over N sine pi P goes to, this eigenmode goes to K over N, so it goes pi P divided by K, well, it's called K over N finite. I'll call it omega or something. And so basically this sign disappears and you get this up to factors, and that's exactly the corresponding solution. Anyway, that's sort of what I vaguely remember about all of this.
Yeah, and you have to be careful about units depending on what constants you're setting to 1 or whatnot. But
yeah. And so, and in this limit, you had xj double dot is equal to minus k squared sine squared omega, something like this, pi p over n or something. And then times x. And in the continuum limit, this becomes dt squared x, dt squared x.
dt squared x.
And then this, you put in this eigenmode frequency, which now becomes this beast, is minus, whatever it is, pi p omega squared times e to the 2 pi I omega p times x, and so you see the satisfies dt squared of x minus dy squared of x up to signs and factors is equal to 0. So basically that's the sort of standard continuum limit of a bunch of oscillators. I don't know how you get a mass in there. Is there an obvious way to put a mass in?
You mean to get a massive?
Yeah, that's a massless wave equation. I was just wondering whether there's a way to put a mass. Do you have to put a viscosity into your damper system or something?
I suppose this is the probably the easiest way, right? Just get a some kind of a potential for, or
yeah.
Anyway,
anyway, that's sort of the standard way.
The viscosity. You were asking how to get a mass term in the wave equation.
Mm-hmm.
I was just curious. I was just as I was doing that.
Something you can do with springs itself.
You can't do a
You
spring.
have all these balls, and they are joined by springs, right?
Mm-hmm. Yep.
But suppose each ball had a mean position, the starting position, but was joined to that position with a spring.
Mm-hmm.
So then there's some springs between the balls.
Mm-hmm.
That is xj minus 1 whole square, right? That's the relative difference between two balls.
Mm-hmm.
But if you also add a term, some 1/2 k prime xj square.
Oh, good. Okay. Yes.
Right. That means that the xj doesn't want to go away from 0. It's also joined by a spring to its own position.
Yes. Good.
So
Okay.
Start with lots of points.
Yes.
There's a ball attached with a spring to each position.
Mm-hmm.
And then with some other spring constant, each ball is joined to the next ball also.
Right.
So if you join a ball to the next ball, that is xj minus 1 whole square.
Right.
But when you have the ball joined to its own position, that is just xj square.
Yeah,
so the coefficient of the xj square sets the mass of the scalar field. And the coefficient of the xj minus 1 square, well, that's the gradient term. So that will help you get what is the speed of light here.
Right.
So I think this is beautiful. What you did here is everything that you had to do. I was just curious, whenever I teach QFT, I actually start here because I don't have any other way of understanding QFT. I always think of, balls joined by springs, and you shake one ball in one place, and you can see the waves sort of moving along the springs. And that's the wave going at the speed of light, or just dispersing if they all have masses. And there's actually nothing else to QFT. But I was wondering, where do people start? Is this something which is standard? Do all QFT courses actually do this?
I don't think they start necessarily here, but they do tend to. They do start with a free massless scalar field usually. That's a fairly common standard starting point. So this is even more basic. But this is I think, if you do a sort of third year of undergraduate physics, this is one of the things where this is baby quantum mechanics, and so therefore this is what people usually start with. So this is the kind of thing I start my string theory course with.
Right. So I think this is nice because this is just, what we've written here. Nothing. The wave equation you have there. If you had to take this wave equation you have in your last line, mm-hmm. and you had to put it in a computer to solve it, mm-hmm. what you do is exactly this, right? You first have to discretize your space into a finite number of points because
mm-hmm.
otherwise you can't proceed. So you have a finite number of points,
yep.
And then in each point you have to put the kinetic term is just del t square. So you'll say, okay, I have some variable there which is the phi dot square. And then the grad phi square is just the value minus the value at the previous place. So if you ever had to put a scalar field on a computer, well, this is what you would do.
Yeah.
So whatever we are calling x, you can call it phi if you like. Mm-hmm. So the xj is the value of phi j. You can either think of it as a vertical displacement or a displacement in the x direction, but that's just words. There is nothing to a scalar field which is not just balls and springs. And actually, not only the scalar field. Every field is basically balls and springs. I mean, if you had a graviton, okay, every transverse direction, hij, every transverse I and j, it basically satisfies box equals 0 in the appropriate gauge. So there is nothing to any part of QFT or string theory or GR or anything which is actually not captured here. So I always think in terms of this. Somebody says, I have a scalar field on a manifold. Only thing registers in my brain are balls and springs. So, and as the space-time stretches, okay, I just see everything just moving apart. But I was just wondering, how do you people think about QFT? I mean, is there some other fundamental way to start with QFT? Like when you have quantum mechanics, to jump to QFT, what is the jump?
I always think one of the main differences between quantum mechanics and QFT is the role of position. Like in quantum mechanics, the role of position is probably like one of the is the field in quantum mechanics, whereas in quantum field theory, the position is just a label, right? Where we think of the field. So for example, here we had like xj, which is the position of the spring of the jth spring is the field, but it's also a position, right? Yeah. So this is kind of like, for me, this was one of the most conceptual like differences of thinking about stuff.
But if you're a relativist, that's just the transition between the manifold and the tangent bundle. I mean, the displacement of X is simply a tangent vector, and it lives in a different space compared to the space-time. So really these XJs are displacements, and therefore they're tangent fields to the manifold. And so therefore I'd say, yes, okay, X is a position, but really there's a position and then there's a displacement about that position, and that's the field, and that's a tangent vector or a cotangent vector. Yes. So, I'm not arguing with you. I just think there's another way to think about this, which is, but yeah, I think, I mean, for me, the thing that separates quantum field theory from quantum mechanics and makes it much harder is, of course, the whole renormalization thing, the fact you've got an infinite number of zero-point energies to start with, and therefore you have to then renormalize the energy, and you have to do cutoffs, and you have to, that's where field theory starts breaking, all hell breaking loose for me, which is what makes it different from just simply a bunch of harmonic oscillators. I don't know. Any other comments?
Yeah, I have a question. So we take n to infinity, which essentially translates to taking the spacing between each little mass to zero. But what if we think in terms of Planck length as sort of the limiting point? In that case, it remains at this sort of a discretized system. So just your thoughts on this.
Well, that's, I guess, the scale, any quantum field theory comes with a cutoff usually. And so you had to put a cutoff in, and sometimes you put it in artificially to regularize it. Sometimes there's a natural one. And so I would say the thought that you're expressing is precisely the fact that for a quantum field theory, you have to cut it off in order to make some kind of sense of the vacuum energies and all the other renormalization structure. And the ultimate cutoff in string theory or gravity is the Planck length. I don't know. Any other comments, Samir? Do you have?
Yeah, I think you can. I think what you're referring to is correct. Yeah, I mean, taking n to infinity. This is a very very simplistic picture, but already you can very easily see that taking this n to infinity without thinking much deeper about it does lead to a problem, because if you write down the Hamiltonian in terms of creation and annihilation operators of this theory, after you have gone to the continuum limit and you have done second quantization, you realize that you have a term in this Hamiltonian that gives you infinity, which is the vacuum energy. So which tells you that, as Nick was saying, yeah, when you took that limit, something happened that you need to fix. Yeah, and yeah, later in your QFT life, you start trying to deal with this. Yeah, this term where Nick has had omega to 0 here. Omega to 1. Yeah. Omega to 1. Whatever.
H bar omega, I guess.
Yeah, H bar omega. Yeah, in so whatever units.
That's always the problem. Quantum field theory, you have an infinite number of degrees of freedom with an infinite number of ground state energies. And that's the beginning of the discussion of renormalization for me. And so the question is, how do you deal with this? Well, the standard way to deal with this is you put in a cutoff, and then you talk about volume renormalization, and then you sneak out your zeta functions and you calculate. But there's a bunch of, this is the standard thing. I mean, when you do string theory, you have exactly this. You have an infinite number of oscillators, and so the regularization of this term is precisely what gives you the intercept from zeta of 0 or something, which gives you the intercept in the string theory, the ground state energy of the string. And so you have to sum, 1 from n equals 1 to infinity. There's a correct way to do this, of course, and that's, but the cheap trick is to use the zeta function.
There's also a question in chat.
Oh, I think that was the same question. I don't know.
Was it the same question?
Any other questions or comments? Sorry.
Oh, it was the same question. Okay.
There's a really fascinating thing underlying exactly the kind of thing which this question was asking and what Nick just said. It's been bothering me continuously, like for the last 30 years. try to make a model for the universe. Let the universe, let's say, be something finite for convenience. Let's take a closed universe. Then you have a certain number of lattice sites. Suppose you thought Planck length was actually a cutoff. Okay, so suppose you have, when the universe is 1 centimeter big, you have 1 million lattice sites. Okay, with a Planck cutoff or whatever. Then the universe expands. Okay, if you still want a Planck scale cutoff, now you have 2 million lattice sites. So if you ever try to model this by something with a finite dimensional Hilbert space, you can't, right? Because now you need the dimension of a Hilbert space cannot jump if you're trying to do any quantum theory. So somehow you have to start with something which, as it expands, either it borrows degrees of freedoms non-locally from other places, or you already had an infinite number of guys to start with. So somehow, if you want to discretize something and you say Planck length is the cutoff, like in some sense it can't be, right? Because then the universe can't expand. So there is some fundamental way we have to think about, like exactly what we just said. You can make a lattice model of QFT as long as space is not stretching. And I've always been happy with that. And then when you start stretching space and you need new degrees of freedom, I just can't understand what to do. So clearly some beauty of string theory that's able to, create new stuff as you go along.
But isn't that just simply the statement that, you have to understand physics as the scale of your cutoff runs? And so that's the whole point of renormalization group flow, that, you have, some set of degrees of freedom, which you choose a cutoff, and you do the Wilsonian thing, you integrate everything below that scale out, and you keep the larger scale stuff. As the universe expands, you just adjust the scale.
I actually have a comment on that. I mean, the moment you set the scale, you also set your boundaries. So if let's say you begin with quantum field side, and so your scale is, like you said, you define your cutoffs, but then that limits you. You cannot then you are not able to then understand how you may be able to go back to, say, classical. And so that could be, these scales on one hand help us do things, but on the other hand may be stopping us from seeing the big picture.
No, the scale in QF, the quantum field theory, is the scale at which you're observing the universe. So in the particle accelerator, this energy scale is set by the dial on the machine. And in the universe, I guess the energy scale is set by the Hubble time, or the Hubble constant. And so the fact that it's changing is no more mysterious than the fact you can turn up the energy on your particle accelerator. Isn't that, maybe I'm missing some deeper philosophical point you're making, Samir, but, the universe is, expanding, sure. And the guy at CERN is turning the knob up and increasing the TeV. And physics, a good theory of physics tells us how to explain what happens when you crank the energy scale up.
No, that's fine. I wasn't disagreeing with that. So normally in QFT, we do have the idea that the cutoff goes all the way to zero size, right? Mm-hmm. It's only if you try to somehow naively think of quantum gravity as saying that Planck length, like there's nothing below that. It's like a lattice spacing. If somebody tried to say that, you get into trouble. Yeah. Because then you can't go below that, right? So then if you say, okay, at Planck length, I have a lattice spacing and I really have a crystal of Planck scale. If you try to do that, then you're stuck. I mean,
okay. So
theory doesn't have that, right? You can go all the way down to zero.
Can I put it another way? The physics that we see today at the Planck scale is deeply sub-Planckian in the early universe, and that's the problem we're worried about.
Absolutely, you can put it exactly that way. Yeah.
Okay.
By the way, I want to mention this book. If you
you're not going to sell us something, are you? No, sorry. Go ahead. It looked. You just came at this like it was an infomercial.
So there's this book by Lancaster and Blundell, and this one actually starts with quantum field theory exactly in terms of balls and springs. So
okay,
so I think it's sort of a more easy introduction to quantum field theory for the gifted amateur, and I liked it quite a lot because it actually starts with the balls and springs, but also does everything else in a simple way. So if anybody wants to see a textbook treatment, they can look at that.
Okay, so I think I want to keep the trains on time so we don't go past 1700 hours locally.
Yeah, do people have any questions about question one? If not, I guess we can move on question two then.
So that's the current state of frequency change, yeah.
Yeah, so go on, Nick, yeah.
No, I was just reminding myself what the question was. So I've got this. Let me put this question up. So question 2. There we go.
Nate, do you wanna?
There it is.
Talk about this. So this problem is basically you start at sometime t less than 0, and you have some single harmonic oscillator, and then at t equal to 0, you change the frequency suddenly, and so you basically want to find out what is the when you change the frequency, what does this do to the vacuum? And so you can start by sort of writing. So you can do this in 2 pictures, I guess. There's the Schrodinger picture and the Heisenberg picture. I think if you consider that the field doesn't change a lot right at near t equal to 0, I think you can use the Schrodinger picture. So you can start by writing your X and you can quantize the theory. So you can write your X and P operators in terms of A's and A daggers. And you can then you define what is the vacuum. So it's when A on the vacuum is 0. So and then you can say, let's consider right after t equal to 0. You could also write this X and P in terms of some B's and B hats or some new oscillators, and you can say, well, the state doesn't change instantaneously, and so near t equal to 0, you can sort of equate the old oscillators to the new oscillators, and you can find the expression of maybe the creation and annihilation operators before t equal to 0 in terms of operators after t equal to 0. And this is in essence this the idea of what we're going to see later is this Bogolubov transformation. It's basically how you relate a basis at one time with a basis at another time, but here they're matched at t equal to 0, and what you can see here is that what was an annihilation operator before t equal to 0 from the perspective of after t equal to 0 is not necessarily an annihilation operator anymore. So this is kind of how you see the beginning stages of what we'll see is like particle production, but in this case it's like sort of excitation of the ground state that was a ground state before t equal to 0. And so with this relationship between, so I guess you could say, you know, a hat, for example, is equal to alpha times b hat plus beta times b hat dagger. So this is sort of a simple case of what you would get, and where the b hat and the b hat, these are the operators corresponding to the frequency after t equal to 0. And so you can write an expression, you can find the relation between the two just with some of the algebra, and you can also show that if I act with a hat on the vacuum of the oscillator before t equal to 0, then using the relationship with the new oscillators, you can actually show that the state with respect to the new oscillators looks like something called like a squeeze state. And let me see.
I'm scribbling as you go, trying to keep up.
Sorry. Yeah.
You're doing a very good job, Nick.
Yeah, I know. This is stuff I know, but I'm going to get all my factors wrong. So let me just say a couple of things. So yeah, the whole point is that you have the original guy with the original frequency, so original creation annihilation. Then you've got new annihilation creation with a new frequency. But the whole point is that Q is proportional to a plus a dagger. I think it adds up.
Yeah.
A plus a dagger.
Yeah.
So therefore, you can put the shift in here by mixing a with a dagger. And so at the end of the day, B becomes a linear combination of a and a dagger, or more importantly, for what I'm about to say, the annihilation operator A is a linear combination of B and B dagger. And so then the vacuum for the A guy is some operator acting on the vacuum for B. And the standard way this comes about is that the vacuum for A is given by the exponential, and there's some constant I'm not going to get right. And then it's acting B dagger acting on the vacuum for B. And where does that come from? Because basically, morally speaking, B is like the differential operator DDB dagger. And because it annihilates B. And so you see that if you have B, alpha B plus beta B dagger on the vacuum for A being 0, then you see that gamma is proportional to something like beta over alpha.
To alpha, I think.
Yeah, something like that. So this is the so-called squeeze state. It's two creation operators. And so by having this is the Bogoliubov transformation. It simply says that the old vacuum, or the old operators are related by a linear combination of the two annihilation creation operators. You've redefined the vacuum for the new system, because this is defined to be the thing that's killed by B. But now there's an operator that creates the vacuum for A, and it's an elementary exercise to solve what is effectively this first order differential equation to deduce this exponential form, which is that. Okay.
And if you want to convince yourself that the thing on the right hand, if you want to convince yourself that the two things are equal, you can act with some B on 0A, and then you can expand the exponential in series, and you'll see what the answer is.
The statement, this is sometimes called Bargmann representation, but the fact that B dagger, normalization's all screwed up, but the fact that B commutes with B dagger, which produce 1, means that morally, in terms as an operator, it behaves like DDB dagger, and you see that DDB dagger acting on this exponential gamma B dagger is simply equal to minus gamma B dagger e to the minus gamma B dagger. And that when you take, so then when B hits it, you get this, and when this hits it, you get this, and up to factors of 2 and crap, you find that the gamma that turns up here is the ratio of these two quantities. And most particularly in this mixing story, the mixing here, beta, I said was proportional to the frequency shift. And so that means this quantity up here is proportional to the shift in frequency. So if there's no frequency shift, the vacuum stays the same. And if there's a frequency shift, you get this thing. Sorry, anyway, I've scribbled like crazy, but I hope that's...
That was great.
I did do my homework at some point, but since I got the iPad, I thought I'd do it. Sorry, go ahead, guys. So let me shut up. There's lots of questions in the chat, I think.
Are there? Oh, yes. Let me see.
Let's see. Oh, okay.
Joseph, you are wicked. Did you put the entire book in the chat and deprive?
It's a Romanian version. Copyright laws don't exist, so. Romania, I'm not under.
You realize you have recorded your criminal activity for everybody to see.
Yes.
Okay. So anyway, sorry, over to you, Sean, or whatever. I'm going to stop sharing.
There's a question in the chat about.
Yeah, we're reading that.
Squeezed states.
Yeah, maybe I can say something about that question. I was about to say something about squeeze states anyway. I think I need some. Okay. Shall I share? Because that will delete the other share.
Yeah, no, that's fine. I've stopped sharing. Go ahead, Samir.
So let me see if I can get my iPad connected.
In principle, Samir, you're a co-host, so you can actually bump into anybody's share and you can just stop them from sharing. So people who are host or co-host, they can just bump in and start sharing on top of other users.
I just try to figure out how to, give me a second to connect this.
Actually, I think it's the answer to your question also about who thinks about quantum field theory this way. I think Feynman's lectures on physics, volume 3, does exactly this kind of stuff with phonons. Anyway, go ahead. Ah, okay.
Yeah, so I just want to reiterate exactly everything that Sean said in just one other language, which might also answer the question which was in the chat. So I always think of the potential of a harmonic oscillator. Let's just draw it. So that's the half k x square. And then the wave function for that is sort of like this, right? I just think of it in pictorial terms. So that's the wave function psi of x. And then if you suddenly change the potential from a half k x square to a half k prime x square. And so let's suppose the new potential is steeper like this. Now the state doesn't suddenly change. So at that moment, the state still looks like this. And so whatever the state is, it is not the ground state for the new potential, because the ground state for the new potential would be something which is like this. It's very sharply peaked. So if it's not the ground state, it has to be an excited state. But every excited state for that potential, suppose for this one, it was written as A and A dagger, as Sean was doing. Suppose for the new potential, I write the states as B and B dagger on the new vacuum everything. Now, if I try to write it, it's not going to be the B vacuum OB. It won't be that, because the state is still the old vacuum OA. The state hasn't changed, but whatever it is now, if I want to think of it in terms of the B oscillators, it will be a little bit of the B oscillator plus maybe some excitations on the B oscillator. And maybe more. And then the reason I don't get the odd terms, in principle, I could try to think about the odd terms also. So there are coefficients here, let's call them alpha, beta, something. But the reason I don't have odd terms is because the symmetric state stays symmetric. So that's why you don't get any odd terms. But clearly you can see you've gotten excitations. So then you might ask, why do you want to write in terms of the B oscillators? And that's because if you want to wait to see how this guy evolves, well, it'll evolve in terms of the frequency for the B oscillators. So each of them will then change in a phase appropriate to how much energy they have in this B basis, and you will get the evolution. And interestingly, if you do it the other way, if you like, instead of making the potential steeper, suppose you made it more shallow. Suppose that's the new potential. But the state has stayed the same as we said before. Even then, it's an excited state. And how do I know it's an excited state? Because it's not the ground state. Because the ground state for this new, this very shallow potential would actually have been something like this. So if it's not the ground state, again, it has to be written in terms of excitations. So it doesn't matter whether you make the potential steeper or shallower, it's going to get excited either way. And that's the beauty of it. And the reason we call this a squeeze state is because the ones that they were making in condensed matter physics were, if they had this potential and the basic vacuum ground state was like this, if you make a state which is much steeper, then they call it a squeeze state. Actually, they're both squeeze states, whether steeper or shallower, if it's not the vacuum, but otherwise it has the form of exponential e to the power some number times a quadratic on the vacuum, then all of them are called squeeze states. So there's a beautiful thing about how you could find the average energy of a squeeze state as a function of this parameter mu, what's the time evolution of a squeeze state, and exactly as somebody was saying right now, the best thing to do is to just expand this in a power series and use B commutator B dagger equals 1, and then everything just comes pouring out. It's just beautiful, beautiful algebra. Just one more comment I wanted to make on that. It's very interesting how the thermal density matrix looks in the same language. Because if you look at what a thermal state is, in a thermal state, everything is actually weighted by energy. So if you have e to the minus energy of some state over kT, that's the weightage of a state. So if I take e to the power minus some alpha B dagger B acting on the vacuum, now this counts the number of excitations, right? So if I want to weight everything by their energy, if I put e to the some constant B dagger B, well, that's the kind of weightage you get for a thermal state. Right now, we're talking of states which have e to the alpha B dagger B dagger. So when you actually go to curved space and, B's and B daggers, you get linear combinations of creation annihilation operators. It's interesting that you always stay in this class of states. For example, what we call exponential of quadratic, e to the power anything of b, let's say phi of x. Now you can convert them back to position. The scalar field at x, scalar field at x prime with some kernel, shall I call it k of x comma x prime, integral dx prime. Now I have many oscillators there because I have a variable at each point. These are exponential of quadratics. Any state you write of this kind, it includes thermal states, includes states you get by pair creation, of course includes the vacuum because you could just choose the vacuum also is also a Gaussian. But the beautiful fact is any evolution you do in curved space, if you start in this class of states, which is exponential of quadratic, the vacuum is a special example, but thermal states are also an example, you will always stay in this class of states. And so somehow it's a beautiful class of states. We have exponential of a quadratic, thermal states are there, like we just said, the kind of states we're getting right now in terms of harmonic oscillators are also there. So it's just a beautiful class of states to get thoroughly familiar with, and everything that's ever done with the information paradox is of course all also contained in here. Okay, that's all I wanted to say. So let me get out of
leave that up a second. Oh, sorry. Okay. So I just wanted to, can you put that back up again a second? Okay. With the picture? I just wanted to make, since it's a tangential comment, but since you said it, I can't resist it. It's the picture at the top. Maybe I should just draw it. Oh. Your screen sharing seems to, oh, there we go. The potential at the top. This, no. Okay, either will do. So this is also a really beautiful story in terms of cosmology. I mean, if you think about what's happening in the early universe, you start getting lumps in the cosmic microwave background, lumps in the material. Sorry, not in the cosmic microwave, in the matter. But as the universe expands, effectively there's a gravitational potential well that's getting flatter and flatter and flatter. And so what's actually happening is those lumps then expand out into excitations. The expansion of the universe itself, the Hubble parameter, acts as a viscosity. And so really what the study of the inflationary scenario is precisely the study of what happens to precisely these kinds of lumps in a potential that's broadening and spreading with a viscosity. So, you know, this is exactly how you understand things like baryon acoustic oscillations and everything else. So it's a beautiful story. So these things are all over physics and they're well worth looking at more generally.
Right. I mean, the source of all these fluctuations in inflation, as Nick is saying, is exactly this. It just start from the vacuum, and then they actually become your particles.
But also, I wanted to say that also they are precisely the dynamics of these squeeze states as it relaxes is precisely well, exactly the same as what creates this fluctuation spectrum in the cosmic microwave background. Because these things relax, you know, the lump is a clump of matter, the potential is the gravitational self-attraction, which is diluting, and the viscosity that's added comes from the Hubble expansion. And the end result is you get the baryons move backwards and forwards inside this potential well created by the dark matter, and that well is then expanding and freezing out. It's exactly the same physics. Anyway, it's tangential, but I thought we should play tourist since we're...
Yeah, that's great. So shall I just stop this share now?
Yeah, so I think we've done problem 2 today.
That was very nice, Samir. Yeah, I mean, in the chat, so the person was asking what might trigger such a transformation. I think Samir gave already one example. If you're considering phonons in these vibrating oscillators, changing the spring constant, if you have some mechanism in your lab changing the spring constant, that would can induce such a change. I don't know, if you're doing an experiment with electrons and holes, I presume changing the potential difference in your experimental setup will induce a similar change.
Actually, there's a calculation you guys are doing, which also is using the same thing. If you drop a string into a black hole, the tidal force changes the effective potential felt by the string. The dramatic thing is when it turns upside down, but you can also get this squeeze state phenomenon as even if the tidal force doesn't overcome the string tension, and you can actually excite the string by squeezing it or stretching it. So it's the same deal. It's just any physical system where you change the spring constant, which can be done by gravitationally. Baryon acoustic oscillations, another example.
Does, for example, if we have a system that's in a false vacuum, if it tunnels to some true vacuum, is that possible to also, you know, to a different potential where like you have a similar change?
I think probably that at quadratic order that's true, but if you at nonlinear orders, I suspect that's not true.
I think that may be more that may be different. If you're tunneling through a barrier, that's not linear physics.
Yeah.
I mean, I think there you're just asking about bubble nucleation. Is that what you're asking?
Oops,
Sorry,
we lost
I
you,
couldn't
Sam.
hear you. Something.
Are you asking about like bubble nucleation?
Well, I wasn't thinking of bubble nucleation. I was just thinking of the Higgs tunneling to a vacuum or something. But yeah, I mean, any kind of semi-classical tunneling.
So I'm not sure what happens there. This is the physics which you get when you write a free field on curved space and you change the geometry of the curved space, but remains a free field. It's just that the metric is changing. So you're writing box
Yeah,
phi,
that was my question.
but the metric coming in phi is changing. Anything which can be put in that form, that is captured here and completely captured here. There's nothing beyond this. But
Yeah,
if
that was
you're
my
in
question.
that situation, then I don't know.
Okay, but that's again tangential. So yeah, and then the second part of the question, I personally can't really answer. Is there a conserved action we need to be thinking about, which might be putting additional constraints on the problem?
So I don't know of any. I don't think there's anything. There is a conserved dot product in curved space, which is actually used to compute these things, and you'll probably be seeing it in your next problem or something. There's an inner product between field modes, which is conserved, but that's just the property of a scalar field. When you expand a scalar field in terms of a complete set of modes, there's the normal Klein-Gordon non-positive definite inner product between them, and that inner product is conserved as you evolve. So that's actually used a lot in the quantum fields and curve space. But as far as I know, that's all that you can have.
Yeah, if somebody has any more questions,
I think we should probably move on to the next one. Otherwise, we'll be here
for a long time. Yeah.
Yeah.
Okay. Next, they want to do 3, or shall we not be alternating like that? Or
sure. Let me just check. Oops. Yeah. So problem 3 is. Let me see. I have some notes, but I don't. Let me see if this is the problem where I got slightly off track.
It's the one where the cosmological scale jumps.
Yeah. So let me see. No, I have my notes, but I don't know whether my notes are okay. Because the notes might be. Anyhow, yeah. So just to introduce the problem, what we're doing is we have this 1 + 1 dimensional cosmology, and this is one of the examples where we can have this change of frequency in a cosmological example. So what we're thinking about is we have a circular system. We have a circular system which at negative times is at some radius, and then at time t is equal to 0, it suddenly jumps to a different radius. And then basically what we're thinking about is we want to have a free scalar field with mass m, which is in a ground state at t at negative time, and then at what happens as time goes to as this jump of the radius comes about. And so basically this is an example. This is kind of like using both of the ideas of problem 1 and problem 2. We have a free scalar field which we need to quantize on both sides. We know how to do it, how to quantize it at t is negative and t is positive. And then again, because of this jump in time, this will effectively, what we will find is, if you remember when we quantized the first system, we had the discrete spectrum of frequencies that were allowed because of the periodic identification. And this periodic identification had 1 over dependent on the radius of your spacetime. So it will depend on A1 or depend on A2. And this change of A1 and A2 will then change the frequencies in which, the natural frequencies in which the scalar field is quantized. And in sort of a way, we'll realize what we've been talking about in problem number 2.
Can I just say, Nick, I'm not sure they're proportional to 1 over the thing.
Well, okay, I'm just doing things quickly as people say things. Okay, tell me if I'm doing something wrong.
I think the frequency is something like square root of some wave
Okay.
number plus.
So let me call it
times
R1 and R2, and then you can figure out what R1 and R2 are in the metric. But yes, indeed, Samir's original statement of the problem involved a change in the conformal factor. So
Yes.
what's going on is that we have a flat metric. So we got some dx squared and minus dt squared plus dx squared, and then there's a jump in the conformal factor. And so the wave operator will go as omega to the minus 2 times ddt squared as ddx squared. And if you put a mass, do I have to put a mass in here? I probably do.
I put a mass,
Yeah, I think
yes.
you can generally.
So I solve that with a mass. And then what actually happens is if I change the conformal factor, what I'm effectively doing is changing the effective mass. So I pull out omega to the minus 2 there, and I get the conformal factor here. So then the moding of this stays pretty much the same. So you mode this with some omega, but then I should say that this gets some e to the I kx. And so the question is, what's omega? Well, the dispersion relation then becomes omega squared is k squared. But now what happens is you have an m squared omega squared. And so when this jumps, it changes the moding. Did I do that right?
Yeah.
Yes.
Yeah, it looks.
Yeah, I think that's right. That's what I understood
You
the
need the
problem.
mass. If you put the mass to 0 in this case, actually there's no particle production.
Yes.
Oh, of course, because theorem, a conformal scalar is conformally invariant and therefore basically doesn't care what omega is. Yes, excellent.
Yes.
So you have to have a mass.
Yeah.
I don't know whatever happened to this, but when I was a graduate student, actually no, it's a postdoc, somebody had the idea that basically we could get out of inflationary universe by massive runaway particle production through this process. I don't know whatever happened to that idea. And that somebody, would you believe, was Nathan Meyervold, amongst other things, but he championed this course. I don't know whether you know the name Nathan Meyervold?
No.
Nope.
No, he was director of research for Microsoft. He's a very, very wealthy person. He was Stephen Hawking's postdoc, designed a mouse for the PC, wrote mouse software, and then got taken over by Bill Gates and became a billionaire. And now he's a patent troll. That I probably shouldn't say on the air, but it's
yeah.
true.
I think we're drifting away from the question, though.
Yes, indeed. But the question was.
So this is, I think here we again can see the same idea as in the previous question, where depending on which side of the t equal to 0 time you are, you get 2 different bases for your oscillator. So the solutions to this equation are just plane waves with this frequency. And on both sides of t equal to 0, you can express your solution in a different basis of plane waves that differ by their frequency. And then you can again express through Bogolov transformations, or just, it's just a straightforward linear exercise. You can express solutions in one basis via the other basis. And then you can match them at t equal to 0 and see what you get for
So I guess it's the same as the previous problem, just a different physical setup that gives you the non-trivial delta omega. Is there anything else you wanted to add about that, Samir?
No, I think, no, that's fine. I think I was wanted to say something about the cosmology case you were citing. People have actually worked out the particle creation during cosmological expansion. It's not much, but does generate a small viscosity on the expansion because some of the energy goes into particle creation, right? So the universe has gets a back reaction on that. So there are lots of papers on this in the astrophysics community. It's not a big effect, so it's not important for them.
It's not. What about when you're inflating it? If you've got Planck scale inflation, couldn't that be a very large effect?
Okay, so I was actually going to talk about the magnitude of that. Let's try to estimate the effect of that. So let me just pose it as a question to people. Suppose you have a universe of radius 1 meter, and it expands to 2 meters over a time scale which is also order a meter. Okay, let's put everything of the same order. So let me ask, how many particles do you think will be created? Just make a guess.
I think it depends on the wavelength of the particle.
Okay, good. What's the typical wavelength of the particle which will be created?
1 meter.
Yeah. 1 meter. Okay, so we have an answer. So for the particles of that wavelength 1 meter, can I ask how many will be created?
One.
One, yes.
There's order 1. There's just one scale in the problem.
Right.
And what will be the energy of that particle? Okay, so that's just 1 over 1 meter.
Yeah.
This is the entire story with the scales, right? So that's all. And now let's go and put it. So suppose you're having inflation. You look at any given volume, then you create, you just double the volume over one e-folding scale. You basically double it. You will create one particle with that wavelength. Okay. So now, if you were at Planck scale, yes, the energy of that particle will be comparable to the energy in that bubble which was causing the inflation. If you're, let's say, a factor 100 below the Planck scale, the energy of this particle will be 1/100th of the energy which is actually doing the inflation. And by the time you come to, okay, so at the gut scale, it won't be much. By the time you come to today, by the time we expand from 3,000 megaparsec to 6,000 megaparsec, you'll create one particle of wavelength 3,000 megaparsecs. Okay, with this corresponding energy. So the effect really drops down very rapidly. So the point is, yes, you will have infinite number of particles created, but per unit horizon size, there's just one, right? So the universe is also getting very big. So per unit horizon size, there's just one. And so the thing you want to compare is the energy of the inflaton field in that region. It's going to drive the inflation compared to the energy of the particle you created, but the whole scale is there. So it's beautiful that came up, because this is something we'll need for the Hawking radiation thing anyway. If you want to know why the wavelength of particles coming out of the black hole is order the radius of the black hole, well, there's only one scale in the problem, and that's the stretching, and that's where it's going to come from.
Okay, so are we done with problem 3?
Yeah, are there any final questions regarding problem 3? Okay, if not, should we go to problem 4? Yeah, so problem 4 is the final example before we get to the paper, which is just 2 harmonic oscillators which are coupled. I think I can even, for this one, I can share some notes, and because I was kind of interested in one question.
Yeah, Nils has a very good question on that one.
So I can share screen. So do you see this?
Yes.
Okay. So this is the problem is this: we have a Lagrangian, which is just two harmonic oscillators which have the same frequency, but then they're coupled with some coupling alpha. I'll change the sign of alpha for further convenience, but the idea is the following. So we have some coupling, which is a time is equal to 0, and then we turn it off. So as far as I understand, this is kind of like the idea of having two particles which are close to each other near the horizon when you take the when you think about the information paradox, and as they get further apart, they become slowly more decoupled. So this is kind of a toy model for that. And once you do this, a nice thing to do is, I can probably get slightly smaller. A nice thing to do is you can decouple them. You can take a particular linear combination in which the squares stay invariant, but then you'll find that the product of x1 and x2 becomes the difference between x plus and x minus. So x plus and x minus is just a plus and minus of x1 and x2. And you find that
comment. This is the standard normal mode expansion for a two coupled harmonic oscillator. X plus is it's got the sum of the frequencies, x minus is the difference of the frequencies or something. So
precisely. What you do is you find the normal modes of this system, and what you find is you get two decoupled oscillators, this time with two different frequencies. One is square root of this, and the other one is square root of the sum and square root of the difference, which we denote in this kind of case. But because these two, now we have two decoupled harmonic oscillators, we can do precisely what we've done in problem 2. These two harmonic oscillators are completely decoupled, so you can quantize them as if they don't exist, they don't talk to each other. And then you got the vacuum, but now what you have to think about is that once you define your creation and annihilation operators, which are these plus, A plus and N minuses, your vacuum now can be excited in two ways. You can have the plus particles, you can have the minus particles. And then you do the same thing as problem 1. This is then becomes problem 2. And you find that once you do this calculation, the vacuum before, when you still have the coupling, and the vacuum after the coupling is given by something which is just this the squeezed operator, where your gamma, which we have, is this particular ratio of frequencies. So once you do this for both of them, you get some kind of normalization, which we don't care about particularly here, but then you get two exponentials, one of them which works on the vacuum of V plus particles and the other one which acts on the vacuum of V minus particles. Now the question is, after we take away the coupling, this still holds, right? So these two normal modes will still be normal modes after we take the coupling out. So these things will be still fine. The only thing is now that we have a different, now the frequency will change. So we have a creation of particles. We will see, we will see non-zero excitations at time is not equal to 0. But what we're kind of interested in, so we see in this kind of case, the two particles are decoupled. Sorry, the two systems, B plus and B minus, are decoupled, but we're kind of interested in the X1 and X2 excitations. Now, remember that what you can think about is that this B plus excitation excites one particle, the X1 plus X2, and B minus excites X1 minus X2. And what you can do is I can define B plus and B minus as just this difference between B1 and B2, which now, because we don't have a coupling in between those two, also B1 and B2 are now decoupled. We're decoupled to harmonic oscillators. But once I expand the exponential, I get B1, the creation of B1 squared. I get some mixed factor, B1 dagger, B2 dagger, and I have B2 dagger squared. And I can expand what I can be interested in what happens if the coupling is very small. And in this case, we find that the sum of these two factors is actually subleading, and the exponential just becomes something which is an exponential of this particle squares, which create one particle, the B1 particle, and the second particle as well. And what this happens is, if you expand this, you will get an entangled state. So basically, you remember that an exponential of two operators is just defined in terms of the series. If you expand this, you will find that first you get, of course, just a vacuum. And then the first non-zero term which is proportional to A, is just one term which has a first particle excited and the second particle excited. So this is what this problem was about, I think. Samir, if you have any comments at this stage.
No, I think that's perfect. That's perfect. Exactly. This is what was to be shown, that after you've broken the coupling, it should look like e to the exponential of B1 dagger, B2 dagger. And that's the part which shows the entanglement. Absolutely.
So my question was, my kind of question with this one is that you have this entanglement only if you consider the particles to be 1 and 2. We found that if the particles, the normal modes are 1 and 2, you'll get this this entangled state. But if I consider my particles to be B plus and B minus, which I can do, I think, because this is a rotation of the because this is a symmetry of the Lagrangian after the coupling is removed, I don't get an entangled state. So I only create either B plus or B minus states. And I was wondering which one is the physical one. So how could I distinguish between those two states after I've taken away the coupling? Between these two excitations.
Yeah, so all I would say is that physically what is happening is that the separation of geodesics at the horizon is the main thing, right? A geodesic just outside sort of peels away and goes far away, and the geodesic just inside sort of peels away and falls into the singularity. That's the separation which is...
Okay, I'm saying, Samir, I think the question was really about, just forget black hole for a moment, just about quantum mechanics. I think Nate just said that this apparent entanglement is merely a basis change, and it goes away if you change the basis.
Absolutely.
So shouldn't we be worried about that? So is there really an entanglement, or is there no entanglement?
So entanglement is always a basis question, and that's fine. It's a basis question, because what is going to happen in the physical problem is that because one of these modes corresponds to particles that have gone far away to infinity, an observer sitting at infinity sees that one. So the fact of which basis you are interested in depends on the physical situation, right? So if the mode corresponding to B1 has gone near infinity, and the modes corresponding to B2 has gone, let's say, deep inside the hole, and you're an observer sitting outside holding the oscillator B1 in your hand, then you're going to ask, what is the state of this B1 if I pass it through a Stern Gerlach and do something to it. But because those are your experiments on it, you actually want the B1 basis. If you actually go to a basis where, B1 was, and B2 was also available to you, and the whole system of the outside and inside was all available to you on the global Cauchy slice, then there is no entanglement to worry about, because the entire system is never entangled with anything. So it's very important to get entanglement. You have to start with one pure state, which of course not entangled with anything. There's always a basis in which looks not entangled with anything. But then the whole point is you're going to divide the system into two parts because of your physical situation. And then you have to ask, is one of these physically separated parts entangled with the other? So if I give you a singular state of 2 electrons, if you are happy with that state, it's just a state by itself. There's nothing wrong with it. But if you now take 1 electron and give the other one to somebody, and then you ask, this 1 electron which I'm holding in my hand, is that entangled with the other one? Well, now your basis is the up-down of electron 1 and the up-down of electron 2. In this basis, you can ask an entanglement question. So the question of entanglement only comes once you're already given a partition of a system. Without the partition, there's no question of entanglement.
There's always an additional aspect to this that comes up in quantum field theory, which is that you're not free to change the basis arbitrarily. I mean, you are in free field theory because everything's harmonic oscillators. But in a quantum field theory, there's a notion of locality and locality of interactions, and that gives you preferred bases. And if you wanted to sort of disentangle an arbitrarily complicated state in the quantum field theory, you would have to use non-local bases of the constituents. And that's sort of not okay.
It's the locality, exactly locality. And once you've gone to infinity, you're holding 1 electron, the one which has come out. That's your oscillator number 1. And now you're asking about its properties, because if you pass it through a Stern Gerlach there, your experiments are on that limit, and your Stern Gerlach will not non-locally touch the part inside. And this is very important because all that we'll see when we come to understanding the wormhole paradigm or the island paradigm is they're actually using exactly your kind of basis. They are saying that think of particles which are in this basis of B plus or B minus, so that they are partly outside and partly inside. Think of it in that basis, and then nothing is entangled with anyone. The problem with that is if you take the particle coming out of the black hole and you pass it through a Stern Gerlach, it will actually show you it's entangled. So exactly, this really codifies the difference between what other people are doing and what the fuzzball thing will do. With a fuzzball, you'll actually get some state which is not entangled, but if you actually get a state where you include both the inside and outside, and you use a non-local basis where the radiation bits and the island bits are all taken as one thing, then there is no entanglement. So yeah, so that's very germane to the issue.
I think I have a very naive question, but I think first of all, so this transformation that Nate did from B plus minus to 1 over square root of 2 times B1 plus minus B2. How do we know that that's a transformation how do we know this B1 and B2 are the B1 and B2 of the system that we started in the beginning? Because before, in the previous questions, the transformation would be something like B plus minus would be equal to some alpha B1 plus beta B2. That is my question: is this transformation that we did just now? Isn't this just some rotation of the plus minus coordinates, and is not actually a transformation that brings us to the problem where we had the alpha in the coupling itself? And maybe we're too naive, and we just get the same answer just because the system is very simple anyway.
I think I understand the question. So yeah, indeed, if you look at the notes I had referred to on my website, I did the thing a little bit differently, though I think the answer is the same. So what Nick did was correct, but I was just doing it differently. I actually kept the oscillators in mind explicitly at all times. So I have started physically with 2 oscillators, right? The physical part is important, that X1 describes one oscillator, X2 is the other oscillator, and then there is a coupling. So when I actually make the excitations of the first oscillator, it's going to correspond to the actual oscillator with variable X1, right? And then with the variable X2. So if you've first gone to some other basis which are linearly mixed, and I agree with you, if you then change things within that basis and get to some new basis elements with that, you don't know if you've actually come down to the X1 variable and the X2 variable. I think that's your question. But yes, you should indeed always look at the X1 and X2 explicitly, and be sure you've come to a basis where you're describing the first oscillator with the first variable and the second oscillator with the second variable. So indeed, one should not just assume that any linear transformation you make will actually put you in this oscillator and that oscillator. But in this case, it just happened to, okay, because it's a simple case. But in general, yes, you actually have different oscillators. And when they were coupled, you could do whatever you wanted. But because you know what is x1, what is x2, you know exactly the physical implication of what describes a particle here, what describes a particle here. And that is crucial to the black hole problem. The particle is an excitation of the fields here. If they're entangled with somebody, that's fine, but they're an excitation of the fields at one place. And indeed, when you get something like particle creation, what you end up getting is the excitations here and the excitations somewhere else are not factored. So the idea of where the degrees of freedom are absolutely crucial, as Samir was saying.
Okay, I think can I continue that? I think I was about to ask, is this linked somehow? And so if we're doing, which I guess we'll get on in the next question, if we're doing QFT curve spacetime, in QFT curve spacetime, once you start doing it, you quickly realize that if you're not in a stationary or static spacetime with a time-like-killing vector field, the notion of a particle becomes a little bit ambiguous and basically arbitrary. But if you have a stationary if you have a time-like-killing vector field, then there is a way where you can, you have a natural selection of what a particle is, and you can define what a particle is. So is this question now with the coupled and decoupled oscillator something similar? So when you have this coupling, is it something about the fact that, like in QFT, it becomes harder to define what a particle, how to define your states in your Hilbert space? Maybe it becomes harder to define your Hilbert space, your Fock space from your Hilbert space. Is it linked to this, or am I just making this too complicated?
It is linked to it, but it's not a problem in the following sense. You have all these oscillators on a line, and it is true you could use any basis, like just as was happening in next solution. You could use B plus, B minus, 3B plus, plus 2B minus. They're all up to you. Whatever you do, it will always look like a quadratic problem. So that's what I was saying before. Once you have a problem which is quadratic in the excitations, x square plus p square, any linear combination of x and p, you can call it b, you can call it a, the whole thing Hamilton will always remain quadratic. Okay, yes. So that way you can use any basis. So while you are in a generally curved region, there is no preferred basis. Okay, that's true. But the following, so whichever basis you use, the answer will be the same. The physics is the same. You can choose your basis. The only reason that there is a good question to ask at the end of this is the following. At least one particle has gone to an asymptotically flat region where you can now genuinely ask the following question. In an asymptotically flat region, you have a genuine definition of particles as that particular choice of basis where the vacuum has zero energy. So if I make a different definition of A and A dagger at infinity, then it will not kill the vacuum. So there's some lowest energy state at infinity. And with that lowest energy state, you define the vacuum. So because at infinity, there's a unique definition based on energy, right? Because infinity is a unique definition. In between, when you slice the whole geometry, whatever definition we're using, they're all going to be fine. And it's not that any one of them is better than the other, and you can't actually choose one. But whichever one you use, the answer to whether at infinity, when you reach and look at a given region of space, whether it actually contains excitations above the vacuum, and the vacuum at infinity is well defined because the lowest energy state, that is a well-defined question. And so there you will get a definite answer. And the answer, what Hawking found was, indeed, there are excitations. And that excitation is entangled with something on the inside, but that something on the inside is not very well definable because somebody uses a different basis on the inside, he will get a different stuff inside. In fact, what you'll see in the Giddings paper is a different basis he chooses inside because slicing is different from the one you will see in my notes. Okay, I prefer my slicing, he has some other slicing. So inside there's no definition of particle. So who you're entangled with on the inside will become completely different for different people. But at infinity, there is no issue. So at infinity, you have a particle, you'll pull it through a Stern lag, you'll find it entangled, and that is real.
Okay, thank you.
Does that answer what you're asking?
Yes.
So in a simplified case, I think in this case precise that we discussed in problem 4, I suppose the correct answer would be at infinity, like if we have access to only one part, like we would act on the final state that comes with, for example, counting operator of the first particle, and that will choose our entangled state, and that will choose the basis, right? And that will give us the entangled state, right?
But I don't want to use the word entangled state. That will tell you what entanglement to look for. I mean,
Yeah.
this is nothing to do with black holes. I mean, even if I give you a big box of gas, it isn't a pure state. I have to define a partition, which might be for whatever reason. I cut it like this or I cut it like this. Once you broke the system into two pieces, you can ask what's the entanglement of one piece with the other piece.
Yeah. Okay. I guess we should move on. Are there any questions on this question? Nick, we can't hear you. You're muted.
I was just saying, I think we should get onto the Giddings paper because we're getting, I don't want to go too much past 1700.
Yeah, okay. Okay. I mean, the Giddings paper is clearly way more work than problems 1 to 4. So I don't really know. I don't think we can like go in a lot of detail. We have already covered, I think, a lot of the basic concepts that are in there, and what I think Samir was saying up to now applies very well to it.
Do you think perhaps, Samir, do you want to point to the paper and say what we should learn from the paper, or for those?
Yes, maybe.
Maybe that's a good way just to go.
I think that's the best we can do. I mean, didn't actually, it's not realistic to discuss the whole paper because it's a long paper. I think the only
Can you share it?
I can share it. Oh.
Yeah, can you put it up or share it? Somebody share it, or Samir, maybe you should share it and then just point.
Samir is talking. Maybe it's better if Samir is sharing it.
Okay.
Okay, I don't have a copy right in front of me. Does somebody have a copy?
I have one. I can share.
Yeah, I've got it. So if you want to put it up, Sean, that's great.
Okay.
Yeah, or you can just put it in the link in the chat, and then I can click it and open it.
Can you guys see?
Yep.
Yeah, okay, that's great.
Yes.
Okay.
So I think everybody should try to work through this paper at their leisure and completely understand the derivation. And the only extra thing you have to see from this is the fact of how you actually define the the field mode. So you have to define this quantum field on curved space has this one mathematical trick that you need to learn. Like normally we expand a scalar field as a hat times e to the I kx minus omega t plus a hat dagger times e to the minus I kx plus I omega t. But this function e to the I kx minus I omega t, that's just a solution of the wave equation, box phi equals 0. So in curved space more generally, you take any set of solutions of box phi equal to 0, you call them f1, f2, f3. And then the whole expansion of scalar field looks like annihilation operators times the f plus the creation operators times the star of f. So maybe that's somewhere. And then I think this exactly the u and the u star here. Exactly. Thank you. So from this, then you simply have to use the fact that u and u star have a certain dot product, which is in equation 3.3 below. And once you have that, this is basically just the different, helps you get the different bases of the harmonic oscillators. So equation 3.2 is telling you exactly what we have done with a pair of oscillators in the previous problem. But then to do it with field modes, it's just like there are more modes, but each mode is a harmonic oscillator. That's what we've learned. And so using this dot product, you convert the field modes to the oscillators, and then the oscillators have the same physics as before. So the beautiful thing is that when you do all that, whatever we were saying in words before, that the particle that comes out is that part of the harmonic oscillator which broke off and the other part went in. Well, now you can see it exactly in terms of field modes. So this is the actual complete calculation. So it's not like we can sort of do it in any particular way here, but this paper is beautiful because it takes you through, whatever Hawking was saying roughly in his paper. I mean, he got all the ideas, but he never actually took the trouble to work it out. But here in the 2D case, it's easy to work everything out very explicitly. And I think everyone should do this once with their own hands to see what the exponential state looks like. So maybe if you go a little further down, you see the state written as exponential of, like in the previous problem, we saw A1 dagger, A2 dagger. Let's go and look for the analog of that. Yeah, so here, thank you, equation 314, you can see it written in terms of creation annihilation operator with some matrix. So you see in equation 314, you see the initial state, O in, state doesn't change in the Heisenberg picture. It's written in terms of the vacuum of the outside and the inside on the right-hand side. That's what you want to see in that. Let's try to write it over the OB. So you have O sub A on the left, you have O sub B on the right. But the final states are, they've taken the vacuum of the out and the in. And then you can see it's going to be exponential of quadratic in the B daggers. And he will actually find it's going to peak at the main terms there are where you have one B from the inside and one B from the outside, one acting on the O out, one acting on the O int. And that's like the B1 dagger and B2 dagger that came up in the toy problem. So the only thing is to figure out this B star A inverse and that matrix in between, because that tells you what the coefficients are. And yeah, so the A and B are there. And so then you simply have to go and find what the alpha and beta are. And now if we go all the way down to section 5, I think we'll see the answer somewhere.
I didn't get this far, I don't think. Okay, section 5. Okay.
Let's keep going. I think maybe at the end of section 5, I think that's his last answer.
Oh, the end of section, okay. And oh,
no, maybe I made a mistake. So
maybe section
so
4.
I actually don't know exactly where it is.
Let me see.
No, yeah, so not section 5, section 4. Yeah, this equation. So this is the density matrix, which you get by when you have two entangled things. In the next problem set, we learn how to make a density matrix out of it. But this is the density matrix. So maybe just above that, let's go a little bit above, we'll see the state. Okay, so if you look at 417, you can see the O in written as an expansion of the extensions of the in oscillator, extension of the out oscillator. Those are the n hats and the n's, and the c's are just numbers, right? So those are coefficients. And then he shows in 418 that those coefficients are exponentials. So then you can see that the whole thing just looks like 419, which is an exponential. That's the e to the b dagger thing we are looking at. But now, because there are many energies, omega j, okay, so they are oscillates for energies, the e to the quadratic for different omega j's, which is like the 1 + 1 cos small g example, because there we had many frequencies and each one was being excited. But there the beautiful thing was, for the cosmology, each Fourier mode separates because symmetry of the problem. So each Fourier mode was entangled only with itself. They just broke apart. Here, we don't have that kind of symmetry. It's not a circle uniformly expanding. So the different Fourier modes can be entangled with each other. But it's still exponential of a quadratic, and it looks like that. So equation 419 is exactly the kind of thing you see in the 1 + 1D cosmology. And then if you go back to the density matrix thing again, just below that, equation 420, that is in some sense his final answer, because if you trace one part out and have the other one left, you can see it looks like a thermal density matrix, because you have it's diagonal, the delta function tells you it's diagonal. So each state is taken with a weightage which is proportional to minus e to the minus the energy of the state upon the temperature. So if you look at that, you can see the temperature is lambda or lambda over 2 pi, whatever is in this case. The summation n jn sum with omega j, the n times omega, that's the total energy. Omega j is the energy of an oscillator. The number of times you excite the oscillator is n. So n times omega is the energy of that oscillator excitation, and summed over all oscillators gives the total energy of the state. So this is just the exponential there in 420 on the right side is just e to the minus energy upon kT. So you read off the temperature from there, you get a density matrix, and this is what Hawking really found, that you have a thermal density matrix coming out of the black hole. So, but you can see that it's actually coming out of entanglement between outside guys and inside guys, and so you have the entanglement. And so what we are supposed to learn from doing this paper and all the problems we had in the problem set is that if you have a smooth horizon, you're not going to get away from this, because at a smooth horizon, you will be keeping on stretching the slices. You start with a vacuum, but you will be keeping on creating pairs. The pairs will be entangled, and your entanglement will keep growing. So if somebody comes and tells you, no, they've got a solution to this and the entanglement doesn't grow, okay, and the page curve comes down, the first thing you're going to ask him, well, how come? If you have a smooth horizon, you're doing the stretching, you'll keep creating pairs of particles. And in this, if you look at this section more carefully, you'll see that the new pairs are, each time you do more expansion, one more particle comes out, one more particle goes in. We'll talk about that in more detail in later sessions as well. You've got to get a very good physical feeling for this. But this is the crucial point. Everybody has to either agree that the entanglement is going up because you're creating these particle pairs, here's an explicit calculation, or they have to tell you what you did. Either you don't have a smooth horizon, which is like in a fuzzball, so you don't have smooth stretching of slices, and then you don't have to have this, or you're going to do something like the island people, and you will say, no, we will get the entangled particles, but what we call outside and what we call inside, somehow we'll mix them up and say that that's the correct basis to think about. And then you have all the non-local issues, because in the particle you're sitting with outside will not behave like a local particle if you pass it through a Stern-Gerlach. So this is very nice, because this really brings us to the net difference between what the island people will be forced into and what the fuzzball people would like to say. So that's all I wanted to say about this, but maybe people can, if they have questions, we can discuss.
Can you just make a quick comment? The scale, or somewhere the dominant scale has to be the mass of the black hole. So where did the scale is obviously lambda here. So
scale is very important. So maybe could I just screen share myself for a second?
Yeah.
I'll just draw the scale.
Let me stop share. Okay. You should be able to draw now.
Let me do that. Yeah, the scale is the crucial thing because that sets the temperature. And in some sense, we already talked about that a little bit. So scale is set by exactly the kind of smooth slices that Nick was drawing beautifully in his thing the other day. So if this is the Penrose diagram of a one-sided black hole, you could draw two-sided. You have a good slice like this, and then later you have a good slice like this, then a slice like this. And the Penrose diagram, they're all squeezed because of squeezing of the Penrose diagram, so it's not clear. And that's why we've actually learned about the Eddington-Finkelstein coordinates, which Nick also took us through. So you have R over here, and there's the horizon here at R equals to M. And the slices look like constant time slices outside. They look like constant space, like R equal to constant inside, and then you can join them like this. But if this is one slice, a later slice looks like this. And then as we were talking last time, don't evolve it much in the inside. In the inside, time goes this way, here time goes this way. So outside you can keep evolving it nicely, but inside we don't want to evolve it much because at R equal to 0, we actually have a singularity. Okay, so in this you can see that the stretching is taking place over a scale like this. And then when you look at the actual metric, you will find that there's only one scale in the problem. The stretching is, let's say, happening, if this is a 3 kilometer radius black hole, when the modes you're looking at are actually have a separation of just 1 meter, they're in the vacuum stage. And then by the time they separate to about 3 kilometers, you end up creating the pair of particles. So then the important thing is, as we were saying before, if you have a curved space of radius 1 meter and you expand it 2 meters over a time scale which is also of order of a meter, you create of the order of 1 particle with wavelength 1 meter. That's exactly what is happening here. So there's only one length scale in the black hole, which let's say 3 kilometers for the radius of the black hole. You can make everything 3 kilometers. The metric only changes on a time scale of 3 kilometers, and you create 1 particle of wavelength 3 kilometers every time the time, as seen from infinity, let's say, increases by of order 3 kilometers. That's all you have to know about in Hawking, the rate of Hawking radiation. In a time of order RH, you will create one entangled pair, and the members of the pair will have a wavelength of order RH. So that sets the scale. So for that, exactly what you will pull out of the calculation. If you look into the calculation, you can see you just have gently curved space with only 1 curvature scale, and the particles are just coming from there. Is that what you were asking, Nick?
Yeah, I was just trying to sort of bring out where the scale comes from in the actual calculation. I mean, it's the basic story that if you look at the sort of Eddington-Finkelstein modes, then versus the Schwarzschild time modes, then when you do the Fourier transform, the difference becomes evident at the scale of the horizon. So, I just wanted to see how that scale was turning up in the Giddings calculation.
Yeah, so it may not be very clear the way Giddings has done it because he looks at the modes all the way at infinity and it may be buried in the Fourier transforms. But the important point is that as long as you are very close to the horizon, you're just looking at a vacuum. What is important is at what distance does the metric genuinely change? Because if you just have a vacuum and just changing coordinates, well, as we said, we change coordinates, you can just write things on different bases. That's not really particle creation. But you can ask, how far do the modes have to get from the horizon before the metric genuinely changes? And that's roughly, let's say, R equals 4m. So at R equals 2m, whatever the metric was, by the time you get to R equals 4m, the metric changes by a factor of order 1. And that's what creates particles at wavelength of the order of m. Once you are at 4m, if you go all the way out to 6m, the metric doesn't change much more, right? It's almost saturated. And to go to 10m, no more change. So once a particle is at 6m, 10m, it's not going to change anymore. But if you follow a particular field mode, a vacuum mode trying to go out, if you are that vacuum mode, as you are going out, you feel the metric under you changing because the metric is changing in the places you're going, and you find yourself being pulled apart. So any field mode here find itself getting pulled apart because the metric is actually changing. So you have to actually look at the metric. You take a Fourier mode and the metric under you is changing, then you'll change into real particles, which is what happened in the expanding cosmology. You took a Fourier mode, it remained e to the ikx for the same k, but the metric on which it was sitting, that changed. So you simply have to ask at what rate the metric under the Fourier mode is changing, and that has a scale RH.
How does this though differ from the cosmological story, where I just simply expand the universe and things get redshifted, and then I just get a different thermal distribution of particles? Well, if I start with a thermal distribution, I finish with a thermal distribution, just at a different temperature. Here, there's particle creation, so there's obviously the scale at which the metric changes isn't the whole story. There's got to be the fact that the horizon generates a non-trivial Bogoliubov transformation.
No, absolutely. So in the cosmology case, there are two completely different effects. If you already had some hot radiation, those real on-shell particles, they will redshift. In addition to that, there will be particle creation, but the particle creation is very small, because if you take a radius of the universe to be 1 meter and you expand it to 2 meters, you'll create of the order of one particle of radius 1 meter. That's what we said. That's the particle creation. But typically a 1 meter universe, it is so hot. It actually contains 1 trillion particles, which have actually come from the hot Big Bang, actually from the end product of inflation. And they completely outweigh the particle production. So in the cosmology, you're not even thinking of particle production. But indeed, the particles you produce by particle creation, even though they are much fewer, whatever they are, they will also keep on getting redshifted, because once they are created as particles, they will get progressively redshifted. In the black hole, once you create them and they reach something like 10 m, the metric under them is not changing anymore. It's not like cosmology. So if at that time they have a wavelength of 3 kilometers, then they keep drifting further outwards, keeping their wavelength of 3 kilometers. So that's the difference between cosmology and the black hole. The cosmology keeps expanding, so the particles you have created, their wavelength will actually keep increasing. While for the black hole, once you've gotten out to 10 m, any further going out, the metric doesn't change and the wavelength doesn't decrease anymore. It doesn't increase anymore. Is that what you were asking?
Yeah, no, I was just trying to clarify the role of the horizon in the story.
Right. So the horizon is very important, because if you didn't have the horizon, so as we said, normally if you just take a star, and suppose the star collapses and becomes like a smaller star, okay, it becomes a neutron star. Okay, the metric has changed from, let's say, a radius r to a radius r by 2, and let's say in a time of order r by 4. Okay, I just put something, everything is order r. You will create just one particle of wavelength r. That has hardly any energy. How come a black hole keeps creating particles on and on till it's completely gone? And that's where the horizon comes in. Because once you have a horizon, you find that there is no slicing of this geometry in which the slices don't keep stretching. If you had a star like this, okay, you can draw a space-like slice. It dips a little bit in the middle. But once the star has stabilized, all the slicing, you can do a slicing, which is all the, sorry, I didn't draw it very well. All the slices are isomorphic to the previous slice. Okay, so if you take the vacuum on this slice, you have a killing vector. The lowest energy state on this slice is going to stay where it is. Now you do it with a black hole and you find once you have a horizon, because space-like slices look like this outside and look like this inside, if you want to complete the slice, it looks like this. If you evolve this further, the next slice is not going to be isomorphic to the previous slice. And the next one will not be isomorphic to the previous slice. Once you have a horizon there is no way to slice the geometry, so that each slice is the same as the previous slice. That's why the particle production keeps going on and on.
So it's your use of the word isomorphic. As far as I'm concerned, those look like completely isomorphic slices. I can map one onto the other.
No, they're getting longer here.
Okay.
They're getting longer. So let's start from the absolute beginning, right? We made the black hole, let's say, at this time. So this time I can even bring them to R equals, complete the whole thing. They are getting longer and longer.
Sure.
And that's the stretching. So that's what's creating the particles. That's the whole point of a horizon. There is no time-independent slicing, because there was a time-independent slicing on that spatial slice, which is the time-independent slicing. You could say, give me the minimum energy state, and you will stay there. But there is actually no time-independent slicing, and you can see the slicing are getting longer. That is the stretching, and that's the source of the particle production. But the stretching is, again, in a time of order 3 kilometers, you stretch by 3 kilometers, you create one particle with 3 kilometers. So it's a slow process, but it goes on. As long as there's a horizon, it will keep going on.
Mm-hmm.
It's maybe useful, just in case people are wondering about it. In the cosmological particle creation example, there's a big difference between something like, radiation-dominated FRW, where there's some kind of, adiabatic change in the scale factor, versus inflation, where there's an exponential change in the scale factor. And so if you're talking about, quantizing harmonic oscillators in this background as the field modes, in the case of cosmologic, in the case of like the, radiation dominated FRW, you're just talking about harmonic oscillators and changing the frequency of the harmonic oscillator adiabatically. Whereas in the de Sitter-like inflation, what's happening is that once a mode gets stretched so that it's outside the horizon, the harmonic oscillator becomes an upside down harmonic oscillator. And so it's no longer just a, frequency, some normal mode oscillation. It's actually an unstable thing. So the amplitude of the mode starts growing exponentially because it's sitting in an upside down potential. And so the fact that you get sort of one particle per Hubble volume is related to this fact that the Hubble volumes are growing exponentially, but the oscillator is upside down. And so, so the sort of number of modes you create in some sense is exponential because the amplitude of an upside down oscillator just runs away. And so there's a big difference between sort of inflationary particle production versus particle production in some order 1 changing scale factor that's sort of smoothly changing over some time scale. So the reason there's a galaxy per every few megaparsecs is because of this sort of like runaway that happens during inflation, rather than having one particle in the entire universe.
Right, you get one particle per Hubble volume at every point, yeah, and then those stretch.
Yeah,
absolutely. So shall I stop this?
Samir, no, can I jump in with a question for you, Samir?
Yeah, okay.
So I think my question is more to do with the gravitational clouds versus the eternal black hole story. So the way I understand it is the reason you have this particle production is because you have a time-dependent gravitational field. That is, you have the collapsing matter.
Right.
If you do not have the collapsing matter, there will be no particle production. So when people consider these eternal black hole scenarios and so on and so forth, why is there? I've always asked myself, but I've been probably too naive. How do they get the Hawking radiation in there? If you start with an eternal black hole, like why is there Hawking radiation there?
Yeah, so actually the eternal black hole also has pair creation. So let me just try to draw the eternal black hole here. Okay, so I'll try to follow next picture. There's the singularity up there, but Nick was drawing the good slices like this, right? So if you try to slice the eternal black hole geometry also by these good slices, you find that later and later slices are actually becoming longer and longer. There is no way to actually slice this geometry so that the later slices are actually going to have the same length as the previous one. So in fact, in the eternal black hole, in this geometry, there's particle creation at both horizons. Okay? So the word eternal is a little misleading. It doesn't mean that there is no particle creation. There is still particle creation at both the horizons. All that is happening is that what people sometimes consider is that what they call the eternal black hole is that you take the black hole and then far away you put a box, let's say, and you fill the box also with radiation at temperature T, the same as the temperature of the black hole. So what is happening is the radiation keeps falling in and the pair creation also keeps coming out. So the mass of the black hole is maintained as m on both sides. It doesn't require eternal hole. Even for a single-sided hole, if you put it in a box at the same temperature, it'll keep eating radiation at the same rate at which is radiating. You can do it also with the eternal hole. But the important thing is the particle creation is still there because there is no way to actually make one slice not the same as the other slice. If you look at the beautiful slicing that Nick had shown in his thing, the slices are getting longer and longer, and you will have particle creation here and here. So even though you can maintain the black hole at a fixed mass, its entanglement with the outside, that keeps going up.
Okay, Samir, but if I go back to without the heat reservoirs, so if I have the double-sided black hole, if I perform the calculation that Hawking did, I should not see particle creation. Where is that going to come? I mean, you're just going to have if you evolve the modes on the infinity backwards in time and you don't have the collapsing region with matter, why am I going to get particle creation anyway?
So you will get particle creation because if you just gave me this geometry, you actually have not specified enough for me to start. Because what I need is also the quantum state at some point. I can't give you the quantum state in the infinite past because there's a singularity. Suppose I give it to you on this slice, which is the most common thing. So suppose I tell you it's the vacuum on this slice. Okay. If it's not the vacuum, of course, there's already some particles there. Suppose you think it's the vacuum on this slice. Oh. Well, in that case, you can now evolve it forward, and you find it at the next time slice, it will not be a vacuum. There will be a pair, actually one pair on the right, entangled, and one pair on the left. Both the horizons will create particles. So you have to also give me a starting state. Now, the only way the single-side black hole was different was that you didn't have to give me a specific starting state, because I could have said, if I make the black hole by collapsing a shell, before the shell, I had flat space. So here, I knew the state. I knew it was the vacuum. So that's just a way of saying that I told you the state was the vacuum. And then from here, I just kept stretching and seeing my pair production. Now here in the eternal black hole case, because the past is a singularity, I have to choose some slice. You could choose whatever slice you like and give you the state. But whatever state I give you, if that is empty, it will be full of particles and more particles as you progress.
I see. Okay.
So the eternal black hole doesn't get you out of any problems.
Can I just, of educational purposes, I just want to interpolate a comment here. Simply, if you think about, the critical thing is defining what the hell you mean, what vacuum you're choosing. And so in the old days, before Hawking's calculation, there was this thing called the Buller vacuum. It's spelt Bullware. But the whole idea is if you take Schwarzschild time, then basically the black hole doesn't create or doesn't produce particles. If you use the Schwarzschild time at infinity to say positive frequency with respect to that time, negative frequency with respect to that time defines annihilation and creation, that defines a vacuum, and so forth, then there's absolutely no particle production. But what happens is if you look at the expectation value of the energy momentum tensor of a scalar field in that vacuum, it diverges horribly at the horizon. And so there were lots of calculations done, where people realized that this vacuum was absolutely awful at the horizon and extremely singular. It was a firewall, to use modern parlance. And so the firewall people really simply rediscovered the Bullware vacuum. It was just simply the statement that if you put structure, if you want to have no information loss, you want to have a good vacuum infinity, you extrapolate that outwards inwards towards the horizon, you discover the horizon's got an incredibly singular structure with lots of states of arbitrarily high energy, some colloquially known as a firewall. So I remember asking a year after Joe Polchinski, after he produced the firewall, well, what's the difference between the Bullware vacuum and the firewall? And the short answer was there wasn't a good answer. So the point being, the Hawking's insight was to say, no, the correct vacuum is the one that is smooth across the horizon. This is why we use Eddington-Finkelstein coordinates. It's the one that connects, in that picture that Samir is showing, it's the one that connects the flat, stop there. The flat before the collapse connects smoothly through the matter to the space-time after the collapse. And it becomes, as you evolve the thing forward into the eternal black hole, if you like, it becomes this good slicing, the vacuum on the good slice. But the critical thing is that vacuum is smooth across the horizon. And that's what really is responsible for making the Hawking radiation in these black holes. So anyway, that was my...
Absolutely, that's perfect. Yeah, exactly.
So coming back to this question of scales, the scale lambda that's inside the Giddings paper, what is that I assume it's related to the mass, but how exactly?
Okay, so this is actually a 2D black hole, and 2D black holes are a little bit unusual in that sense. So lambda is actually going to be the cosmological constant, I think. And all black holes in 2D have the same temperature, and it is actually set by lambda and not by the mass of the hole. These are just peculiarities of 2D. So I think there are some differences from the 3D case that you will notice, but the essential fact that it is something, B dagger upon something which you will call the temperature. I think that's the part which will be universal. But I think lambda will be more like let me stop share and go and look at that paper again. I think
it is the cosmological constant, yes.
Like a cosmological constant.
It is precisely the cosmological constant, or it's like proportional to it. So it is.
That's just the problem of the 2D black hole. Actually, the Hawking radiation rate, if you actually calculate by doing Hawking's calculation, you find it's not given by the mass, given by the lambda cosmological constant.
But it's also worth remembering in that context that if you just forget the sphere, and you just take the Schwarzschild metric, and you take it in these Kruskal-Zeker's coordinates, it's flat space with a conformal factor, and the conformal factor is set by the mass. So it really is, the cosmological problem really is a superb toy model of the R and T dependence of the full black hole.
Yeah, okay, that's great. Thanks.
I personally have another question, but I've been asking many questions. If other people have other questions, they should go first.
Well, yeah, jump in, guys, if there are any other questions. I haven't been monitoring the chat, but there doesn't seem to be anything.
Okay, I mean, I'll go
Go
ahead.
for it.
Samir, so one thing that I noticed when I was reading the Giddings paper and trying to remember what Hawking does in his paper. So as far as I remember, in Hawking, his paper, he does not really refer much to the modes on the horizon, because he takes the mode at no infinity and propagates it backwards in time and works with the modes on Scry plus and Scry minus. Because the modes on the, on the event horizon in the interior of the black hole, you don't have a, you can't really say what a particle is. And in the Giddings paper, they give these expressions of the vacuum outside B equal to some stuff of the vacuum state with this exponential that you were referring to, that has creation operators both for the modes on the horizon and the modes at no infinity, at plus no infinity. And then they talk about tracing this. So my question is, like, how does it make sense to trace over something that's not even well defined? Like, how do you know that you get something that even makes sense to talk about?
Yeah, that's a good question, but it also has a very precise answer. The modes are not well defined in the sense that there are definite degrees of freedom there, right? Every quantum field on curved space is just a bunch of point masses joined by springs. Now, you can take any basis for those degrees. Like suppose I have 10 things here, I can use x1, x2 up to x10, or I can use some other linear combination, like the Fourier modes there. So which linear combination you take, those are the different particle bases. So when you say, I can use this definition of particle or that definition of particle, it is just different linear combinations of the harmonic oscillator variables. But there are no other variables there, because it just started with a scalar field phi of x. And if you look at what you wrote as the Lagrangian, it is phi dot square minus grad phi square. So it is literally just that. So when you say it's not well defined, what you call a particle is not well defined, because what you call A and A dagger is not well defined, because there's no particular choice of basis e to the ikx, which is preferred, which is well defined. But any basis you use, the states are the same. And the point is, if you have two different systems, like I'm holding half a box, you're holding half a box, which basis of states you take in your half of the box, when I trace you out, my density matrix is the same. So that's the important thing. It doesn't matter what basis of states you have in your hand, my entanglement with my half of the box with your half of the box will always give the same density matrix on my side. So that you have to, we'll see when we look at density, definition of density matrix next time, it doesn't matter what basis you are using. So indeed, what you call a particle is not well defined on the inside, and different people have different definitions of particle, but you never even had to go to an A and A dagger basis if you didn't want to. You simply have different points. At each point, you have variables x1, x2, well, phi1, phi2 up to phi10, and all different values of phis. That's your complete configuration space, and your actual state is an amplitude for every configuration. Okay, so that's what a state is, right? You have some configurations for a system, some probability, some complex number for every amplitude. That is a state. That's all you need to know. And which basis you take for that, the density matrix will not care. How much you entangle with that, it will not matter. Like if I have a spin half entangled with your spin half, what basis you take for your spin half will not change the fact that my entanglement with you is low. So does it answer what you were asking?
Mostly, yeah, but I was also worried, isn't it possible that inside the horizon or on the horizon, you'll be able to select modes that have like negative amplitude and things like that are unphysical? If you can't split your Hilbert space in positive and negative energy states and things like that.
So it actually has nothing to do with energy states, because once you have a state, entanglement is just a property of states. It actually doesn't even have to do with energies. And so what will happen is you have a completely good Cauchy slice that cuts across the outside and the inside. These are the good slices that Nick was showing you. So on that slice, you have a state. Right now, you don't even care about its energy. Because, if I give you an entangled state of two spins, if I want to ask you how much is my spin entangled with yours, it has nothing to do with the energy or the Hamiltonian of the system. Right? So there's nothing like a negative amplitude. You have a Hilbert space, it's just a linear vector space. In the linear vector space, you write the total thing as this part times this part plus another piece, this part times this part, and there you have your entanglement already. So entanglement has nothing to do with energies at all. So energies inside can be negative as seen from infinity, but that will not change the entanglement. So the only thing which matters is that the evolution must be unitary, that nothing is getting lost, because if you start losing states, like if I had a box and you had half a box, we were entangled, and then your box of two different vectors just collapsed to one. Now that's not unitary, right? Orthogonal vectors have to remain orthogonal. But suppose you took two different orthogonal vectors and you collapsed them to one. That's a non-unitary evolution, right? If you start doing that, then the density matrix will change, right? I cannot entangle with you if, let's say, you have only one state. So if you had two spin states, you collapse them to one, then it's a problem. But that will not happen as long as you are using the evolution box phi equal to 0. Because if you're using the evolution box phi equal to 0, then exactly by using the Fourier mode expansion that you see in Gidding's paper, like you take a complete basis f and f star, and then the inner product that we have there between them, and you define the field as a times f plus a, then he's calling u and u's and v's. As long as you use this formalism, there's no non-unitarity because every mode is actually being preserved. That's the conserved inner product we were talking about, right? So you have to do consistent evolution. So if you take box phi equal to 0 and you consistently evolve it and you follow the actual commutation relations of the a's and a daggers, you're not cheating. You are never going to lose any states, and you will keep finding the entanglement is growing. The energies can be negative, nothing to do with the energies, but you are having a unitary evolution and you will not lose your entanglement. And in fact, you will see it growing. So it's very important that, so that's where all these dot products come in, right? Suppose you were doing a calculation, you made a mistake with the dot product. You use the wrong dot product. Then it will not be unitary. So we have, but here we are using box phi equal to 0. This is the conserved inner product. And so that's equal to saying that a commutator a dagger is equal to 1. Suppose in the middle you said, no, a commutator a dagger equal to a half. Then you have broken unitarity. So a lot of the papers these days on islands, if you go and look at what they're doing in the interior, they're actually breaking unitarity. Sometimes they say, I will change my dot product in the interior. But when you go and see what they are doing, they're changing unitarity. Two different states in the inside, they're collapsing them to one state. So then obviously that's the same as information loss.
Yes.
So some of those things are information loss scenarios. We'll see that when we come to the papers.
Okay. Thank you. That answered my question very well.
Is there just a nice, I mean, I really like the connection between the little exercises you had us do to start with, and then the sort of final set of the black hole radiance thing. Is there a clean way of talking about, you had this picture of cutting the connection between two harmonic oscillators. Now, obviously, that's supposed to be a metaphor for the fact that things are stretching and getting separated. But is there a sort of dynamical way you see that falling into a black hole does exactly the analog on your springs of cutting the coupling between two harmonic oscillators? Is there a nice way to actually see that?
Absolutely. And the way to see that is that if you stretch a slice, let's write the Hamiltonian. So the spring part is the grad phi square, right? In the Lagrangian, there's a grad phi square.
Right.
So grad phi means let's label the points 1, 2, 3 up to 10. And we're looking, let's say, at the points 5 and 6, which are like just across. 5 is just inside the horizon, 6 is just outside the horizon.
Right.
So what's going to happen is the distance between 5 and 6 will increase.
Right.
So I can just say the metric gxx, let's x be that coordinate. Sure. Gxx is going to go to twice gxx.
Right.
Okay, so that's the meaning of expansion. Okay, let's see what happens to grad phi square. So if you take grad phi square, what is grad phi square? It is phi 2 minus phi 1 divided by the distance between them. Okay, so let's write in terms of the coordinates. In terms of the coordinates, the delta x is just 1. So grad phi square is d phi by dx whole square with g upper xx.
Sure. Yeah.
So if I double the length, gxx becomes twice of what it is, actually 4 times, but g upper xx, the inverse metric, becomes 1/4.
Right.
So you can see that the grad phi square, when you stretch something, if I double the length, the grad phi square actually becomes 1/4 of grad phi square. You can see the spring constant drop to 1/4. That's exactly what it is.
Sure.
So yeah, so the stretching of slices, because the g upper xx comes in the grad phi mod square, when you stretch them, the g upper xx will drop, and so the coupling k has decreased. So we write one field phi at each coordinate point x. The coordinate point, let's just take 10 coordinate points, and then what we are changing is the proper distance between them. And the way to change the proper distance is to change the gxx. And then you will see it's exactly the spring constant changing in the way that we said.
So what about, so all this stuff rests directly on the fact you're using a good slicing. What about using a slicing that just runs into the singularity and declaring, that's the good slicing's just produces nonsense physics, and you simply have to take a slice that runs into the singularity?
It makes no difference. Actually, I think Giddings sometimes takes a slice that runs into the singularity. Is that what he does in this paper? I forget.
But why does it make no difference?
Because it goes straight into the singularity.
Yeah.
And that's completely fine, because what happens to something once it's gone inside doesn't change its entanglement with what is outside.
Right.
So in some other papers of Giddings, maybe not this paper, he takes things and goes straight into the singularity. But whenever something comes out, inside it can get crushed. You can do whatever you want to it. The entanglement doesn't change.
But the stretching, this whole stretching process requires you have the good slice so that you can put large amounts of spatial volume on the good slice. So what about so
that you need. So across the horizon, it has to be smooth, right? So if you take a slicing, which is, the normal flats t equal to constant far outside, then smooth across the horizon. Doesn't matter exactly how you bend it, but smooth across the horizon in a region of, let's say, order m around the horizon.
Mm-hmm.
After that, whether you keep it like asymptotically staying away from r equals 0, like we were trying to do, or you let it run into the singularity, it makes no difference, because the particle creation happens only in the region around the horizon. Yeah. So as long as the slice is smooth around the horizon and the part of the mode coming out, that doesn't care with what you did with the slice inside. You can do anything you want.
But the stretching phenomenon actually happens in the neighborhood of the horizon, or does it actually happen in? That's what I was trying to pin you down on.
You mean the pair creation?
No, the stretching. So the whole idea was that there was a large distance developing between the individual quanta you create. But if you run the interior slice into the singularity, do you still have that large spatial stretching between the two quanta?
You do, because the part which is actually relevant to the quantum that goes outside is actually the part which was always outside. Because if you look at if you follow the modes back from infinity, they come to the outside of the horizon. Mm-hmm. So the part of the mode which was just outside the horizon is the one which is going to get stretched over to the mode which reaches infinity.
Right.
So if you actually want to, so the reason I take it symmetrically across the horizon is so you can just see it more nicely. Mm-hmm. But actually it doesn't matter what coordinates you took or what slicing you took on the interior part. The only part which actually matters for what got created at infinity was the part which starts at, if you follow the mode back, it always actually stays outside.
Right.
So you should absolutely sketch it in various coordinates and see you get exactly the same answer in any coordinate system.
We're past 1700 hours, but any last questions or comments? I think we should, probably people are getting tired, but last questions or comments? Okay, so as per usual, what will happen is Samir will hopefully produce the new problem set during his time during the day, and it'll turn up on the website tomorrow, maybe late tonight, depending on when Samir does it, and it'll go around, and Joseph will email it around, hopefully.
So, I think there's one more question on the chat.
Oh, there's another question on the chat. Somebody said thanks. That's about 7 new messages. Sorry.
All the way down, I think.
So instead, you begin with a particle on the horizon like a meson. That's a tidal force question, I think, rather than.
So it's not really, right? I mean, a meson is so small, like locally in the horizon. So there's a scale involved, as we were talking, right? That wavelengths are small, and then they start stretching over the scale of 3 kilometers. If you just take a particle which is like that small, it'll either go completely out because of the attraction between the quarks. If it's just outside the horizon, it may just end up going out. If just inside, it may end up falling in. Or if it's a massive particle, it may go a little bit outside, then fall in. But the tidal force is weak, as Nick was saying. So it's not like the 2 quarks will get pulled apart.
Yeah, you would need the curvature at the horizon scale to be a Fermi.
Right.
Right. You would need the tidal forces to be of order the string tension of QCD. So the black hole would have to be very tiny. Yeah. This is, by the way, related to something called the correspondence principle, Horowitz and Polchinski, that when the curvature gets to be of order the horizon, so the curvature of the horizon gets to be of order the string scale in string theory, then very interesting and weird phenomena happen. Because you can basically start stretching strings because of the tidal forces at the horizon. And but that's maybe a different story.
Got it. Okay, I think we should call it a day at this point. So thank you, everybody, and particularly thank you to Nate and to Bogdan and to Sean, and of course to Samir.
Thanks.
Another good discussion. So